Okay, so a quick break for another theorem, another important theorem that I want to spend time and actually prove this time before we do a couple more examples. So suppose that you have a function on a domain that has an antiderivative. What's an antiderivative? Well, it's what you think it is. So we're not going to go into the definition of that, but it's in the book. Uh, so what's the theorem? Well, for any contour C in D, with initial point, so the beginning z naught and terminal point z1, so ending point. The integral over c of f of z dz is the f of the end minus f of the beginning. So this should remind you, of course, of the fundamental theorem of calculus. Let's go ahead and prove this real quick. So sketch of a proof at least. So parameterize. I never know if I put enough e's in the word parameterize. Parameterize C. So we have some parameterization that I don't actually care about what the x and y's are, and it's on the time interval from a to b. Then this contour integral is by definition the integral from a to b, f of z of t, z prime of t dt. Okay, that's how we plug in our, we plug in our parameterization into the function and we multiply by z prime of t dt. But f has an antiderivative, right? Little f has the antiderivative big F. So what do we know? We know that big F prime is little f. So we can rewrite this as integral from a to b, f prime of z of t, z prime of t dt. And if we think about that for a second, this is an instance where the chain rule has happened. So this is the derivative of the composite function f of z dt. And when you integrate a derivative, you get back the guy you differentiated. So this is f of z, oops, I don't need the brackets there. This is f of z of t evaluated from a to b, which is f of z of b minus f of z of a, which is f of z1, the end of our contour, minus f of z naught, the start of our contour. All right, so if you have an antiderivative of your function, the value of the contour integral is very easy to compute. You don't actually have to do any parameterizations. And so in particular, if we were to go back up for a minute, this guy here has an antiderivative. It's z squared, right? And so what we should have to do to compute that contour integral is instead, we're going to plug in, let's see, we start at -1 and we end at -1 plus I. So we evaluate at -1 to -1 plus I. So that's -1 plus I squared minus -1 squared. -1 plus I squared you can compute, it's -2I, and minus -1 squared is -1. That's exactly what we found. It's the same thing. So when you have an antiderivative, you can compute, here it is, you can compute the value of the contour integral just by plugging in the endpoint and the beginning point.